Hi, it's Kim. Today we're going to talk about chemical reaction equations and how to translate between talking about a chemical reaction in words and putting that chemical reaction into chemical equation language. It can be really deceptively tricky to go back and forth between these two languages, words and chemical equation formulas. Adding to that, we're also going to talk about how there are different types of chemical equations. There's what we call skeletal chemical equations and what we call balanced chemical equations. It's just a lot of language. And so what I'm going to hope to do in this video is help to visualize what's happening in a chemical reaction in terms of the particles that are reacting and help you see how some keywords in English can be used to figure out what those words mean in a chemical equation. Let's go. Our learning goals for this video are to identify reactants and products when given a skeletal chemical reaction equation, to represent chemical reactions in words, skeletal reaction equations, and particle diagrams, and to explain the difference between a skeletal chemical reaction equation and a balanced chemical reaction equation. Let's get going. In the Haber process, nitrogen gas and hydrogen gas react with each other to produce ammonia. Nitrogen gas is found in nature as generally as N2. Hydrogen gas is found as H2. Ammonia is NH3. So in order to form NH3, this reaction needs to break the bonds between the two nitrogen atoms and break the bonds between the two hydrogen atoms and create new bonds between nitrogen and hydrogen atoms. When we go to translate the words into the structure of a chemical equation where we've got reactants on one side of an arrow, products on the other side of the arrow, I like to kind of go piece by piece and first start by taking out the words that are the different parts of the reaction and writing them out in arrow form. So nitrogen and hydrogen gas react. That tells me that nitrogen plus hydrogen are the reactants and are going to go on the left side of the reaction arrow. They produce ammonia. That's going to go on the right side of the reaction arrow. To write this as a skeletal chemical reaction equation, skeletal just means that I'm writing just the chemical compounds just the way the formula is given to me. I'm not worrying about counting how many atoms there are of each element. So I'm going to go ahead and I'm going to write N2 plus H2 reacts to form NH3. What do you all think that those little parentheses G mean? Look at the words and think about it. Those little parentheses with the letter inside of them, it's often G, L, S, or AQ. Those are telling us of our states of matter. So this is saying N2 gas plus hydrogen H2 gas reacts to form NH3 gas. And then finally, we can visualize this as a particle diagram. This is my personal favorite way to visualize. I can use blue circles to represent nitrogen, white circles to represent hydrogen, and I can sketch myself a particle diagram showing that when two atoms are chemically bonded, they're drawn as touching each other. My reactants, like I said before, are all of my chemicals that are on the left side of the reaction arrow. My products are on the right side. And so notice I can kind of look down the reactants column here and see how the reactants were translated into different forms. Nitrogen and hydrogen are my reactants. The chemical formulas for those were given to me, right? N2 gas plus H2 gas, and then the particle diagrams down below. The words react to form is my kind of keyword to translate into an arrow, and then ammonia is my only product in this example. Let's look at another example using the same structure. So in this example, we're going to think about electrolysis of water. Electrolysis means splitting with electricity. So imagine we had water and we were decomposing it into oxygen gas and hydrogen gas using a battery, using electricity to power that process, to break the bonds between hydrogen and oxygen in water so that the new bonds between oxygen and hydrogen could form. Let's think about what my different components of this reaction would be. So in words, I've got water decomposes. I'm actually going to go ahead and I'm going to start off with water decomposes to form. Water is my reactant, decomposes to form is my reaction language, and then my products are hydrogen and oxygen gas. My skeletal chemical reaction equation, I'm going to look up to the problem, right? The problem is giving me the chemical formulas if they're not chemical formulas that I can get from my reference table or otherwise deduce easily. So H2O, liquid, decomposes, that's going to be the reaction arrow, to form O2 gas plus H2 gas. And then finally, our particle diagram. So I'm going to draw a key for myself so that I know which colors I'm using. And I'm going to say, okay, H2O splits apart, reacts to form O2 plus H2. And I can follow exactly what I'm doing in chemical formula language in particle diagram language as a nice way to visualize what this really means about the atoms that are involved. Let's do another example. Zinc metal and aqueous means dissolved, remember? Aqueous hydrochloric acid reacts to form aqueous zinc chloride and hydrogen gas. Again, we're going to think about our reactants and our products in words, in chemical formulas, and in particle diagrams. So let's think. Reactants. If I go back to the word problem, zinc metal and aqueous hydrochloric acid react to form. That word react to form. Everything before that is my reactants. So that's going to be two reactants, zinc metal and aqueous hydrochloric acid. React to form is my reaction language, and then my products are going to be aqueous zinc chloride and hydrogen gas. When I go to write my chemical reaction equation, I'm just going to go take the chemical formulas as they were written for me in the problem as well. So zinc metal becomes Zn, and it's a solid, so I'm going to say solid, plus aqueous, so that would be the symbol AQ, hydrochloric acid, arrow for reacts to form, ZnCl2, aqueous, plus H2 gas. And then finally, I give myself a little key to represent the various elements here, and I will sketch out my particle diagram following the reaction as it is written. So this number of atoms in each molecule or particle diagram depends on the subscript in the chemical formula.
Let's look at a third example. Methane gas burns in the presence of oxygen gas and releases carbon dioxide and water vapor. This is methane. This is one of the most potent greenhouse gases that is a huge contributor to man-made climate change. We can see here that when methane combusts and burns in the presence of oxygen, one of the products is CO2, is carbon dioxide. So let's think about how we would write this chemical equation in words. So our reactants are going to be, let's read this. This one's a little bit trickier. Methane burns in the presence of oxygen gas and releases. So I know I'm starting with methane because that's the first word in the whole sentence, and it's saying this is what I'm starting with. Methane is burning to release this. So methane and oxygen are going to be my reactants here. If I'm reading the sentence, right, they are the starting materials. So methane gas and oxygen gas are my reactants. They burn and release. Those are my reaction keywords. Water vapor and carbon dioxide. Writing my chemical reaction equation, the chemical equation for methane is in the word problem, and so are all the other chemical equations I need. And all of my chemical equations are going to be in gas form because even water vapor was gas. When I go to draw my particle diagram, a few more particles that are involved here because I've got a lot of atoms in CH4, but it's nothing too crazy. We can take a look and see we've got CH4 reacting with O2 to form CO2 plus H2O. So here's an example of this reaction in words, skeletal reaction equation, and particle diagrams. The next thing we're going to do is we're going to take a look at some examples of skeletal chemical equations next to balanced chemical equations. So here is our first reaction, the Haber process, the synthesis of ammonia. Take a look at the top reaction and the way that that particle diagram is drawn. That is the skeletal chemical equation. I'd like you to notice the difference between that and the balanced chemical equation. So think about it. Hopefully you have a difference that you've identified. Let's look at another example and see if that pattern that you identified holds. So here is our combustion of methane. Let's take a look at the skeletal chemical reaction equation and the balanced chemical reaction equation. See if you notice a difference. Let's look at another example. See if the pattern is continuing to hold. So here's our zinc reacting with hydrochloric acid. Take a look at the skeletal versus the balanced. And finally, our decomposition of water. Compare the skeletal chemical equation to the balanced chemical equation. What do you notice in all four of these examples is different between the skeletal and the balanced chemical equation? So, what did you notice between the skeletal chemical equation and the balanced chemical equation? This is going to be something that you're going to be learning about in the coming lessons. And if you take a look, the balanced chemical equations have some different numbers involved, and the particle diagrams look a little bit different. We'll be thinking about this as you continue on in your lessons, and you're going to hear this term balanced chemical equation again. So I'll just show you again one more time. Notice the balanced chemical equations have numbers called coefficients in front of the chemical formulas sometimes. Notice that. The particle diagrams are also a little bit different. So for extra credit, you could start thinking about why we might need to balance equations. And you also might want to notice in the example of an equation such as this one, where you've got H2O2, hydrogen peroxide decomposing, turns out the balanced chemical equation and the skeletal chemical equation are actually already the same. So they're not always different from each other.
All right, let's check back in on our learning goals. Hopefully you feel more confident translating from words to chemical equations. Remember, it's all about figuring out what the reactants and the products are and where your reaction language is happening to know where to put that reaction arrow. Hopefully you also are starting to get some sense of what the difference between a skeletal or an unbalanced chemical reaction is and a balanced chemical reaction. But if you're not sure yet, that's okay. It'll be something you are going to learn in the future. Thanks for doing chemistry with me today.